Dear student, warm welcome to NPTEL Phase 2 program video course on Geosynthetics Engineering in Theory and Practice. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. This lecture number 47, Module 9, Geosynthetics for Ground Improvement. Now, I will focus recap of previous lecture, design chart with Shear effect and oil resistance, instrumentation of embankment on soft soil with prefabricated vertical drain, installation of prefabricated vertical drain, and now I have complete design example partly covered. Now, this design example, now I will continue in step 8. Calculate the shear strength, that is improve in each stage. So, shear strength improve is equal to Cu final into Nc by Fs. What Cu final is the coefficient after the improvement, and Nc bearing capacity factor is equal to 5.7 and Fs factor of safety. Improvement in shear strength after stage 1. That means shear strength improve is equal to, you know, Cu value is 3.83, Nc value is 5.7, this divided by 3 factor of safety is 7.28 ton per meter square. Now, improvement in shear strength after stage 2, that is shear strength improve, that is 4.9, that is Cu, into 5.7 Nc divided by factor of safety 3, that means 9.3 ton per meter square. So, you can see by stage wise how this improvement in the shear strength value. Improvement in shear strength after stage 3, shear strength improve is equal to 5.7 into 5.7 divided by 3 is equal to 10.83 ton per meter square. Step 9, determine the height of field that can be safely placed on soil for the next stage by following equation. H field is equal to shear strength improved in previous stage divided by gamma of embankment, where H field is equal to height of field that can safely be placed over the soil, and gamma embankment is equal to unit weight of embankment soil 1.8 ton per meter cube. As the shear strength improved in the first stage is 7.28 ton per meter square, so H of field is equal to 7.28 divided by 1.8 is approximately 4 meter. Now, step 10, check whether the shear strength of the soil is greater than the bearing capacity of the soil which determined in step 1 or not. If not, revise the days. The settlement after n number of stages should also be greater than the settlement calculated by the general consolidation theory in step 2. Here input soil properties are given, that is, this is the thickness of the compressible soil layer, that is 10 meter, that is maximum height of the reinforced earth wall is 4.35 meter, live load equivalent to embankment is 2.7 meter, then height of total of the embankment 7.04, density of the embankment 1.8 ton per meter cube, and the density of the compressible soil is 1.2 ton per meter cube, and initial void ratio 1.2 and plasticity index 27. Horizontal degree of consolidation is 2.2 into 10 to the power minus 2 meter square per day, and vertical degree of consolidation is 2.5 meter square per day. So, initial cohesionless of the soil is 2.5 ton per meter square, and factor of safety is 3, and compression index of the soil 0.243. So, we can see that what is the result for stage loading calculation. So, stage loading for the time, that is day, this is the first stage loading for 30 days, second stage loading for 10 days, and third stage loading for 5. And this is the total field height meter. So, initial stage you calculated 3 meter, then second stage is 4 meter, and third stage is 5 meter. So, degree of consolidation you have achieved 0.91, 91% in the first stage, second stage is 55%, and third stage is 33%. Now, initial cohesion C in ton per meter square in the first stage 2.5 ton per meter square, then increased to 3.83, then third stage is increased to 4.9 ton per meter square. Initial shear strength is first stage 4.75, then increased to second stage 7.28, and third stage is 9.3 ton per meter square. Cohesion after consolidation is 3.83 in the first stage, 4.9 in the second stage, and 5.7 in the third stage. And shear strength value, which is important to us, that is in the first stage 7.28 ton per meter square, second stage 9.3 ton per meter square, and the third stage 10.83 ton per meter square, which is greater than 7.4 ton per meter square. So, total height of the field can be placed initial about 4 meter, then 5.2 meter, and the third stage is 6 meter. Hence, provide that 4 and the 5. We have also calculated the settlement in the first stage 410 millimeter, second stage is settlement is 156 millimeter, and the third stage is 70 meter. So, you can add, so you can have the total settlement about 636 millimeter. Now, settlement calculation in each stage, S1 is equal to U percentage into delta 1, P0 is equal to H by 2 gamma of effective, gamma effective is equal to gamma saturated minus 1, and gamma saturated value given 1.7 minus 1, 0.7 ton per meter cube. So, settlement S1 is equal to 0.91 here, and then Cc 0.243, H is equal to 10, 1 upon 1 plus Cc is 1.2 plus log 10, and this P0 is equal to 5 into 1.7 minus 1 plus delta P is 3 into 1.8. This divided by is P0. So, P0 is equal to 5 into 1.7 minus 1. So, you can calculate the S1 will be 0.91 into 447.69 millimeter is approximately 410 millimeter. Settlement calculation in stage 2, that is S2 is U percentage into delta of 2. That means S2 will be equal to 0.55 because U is 0.55. So, Cc into H by 1 plus E0 log P0 plus delta P by P0, this is 0.55 U into that Cc 0.243 into height is 10, 1 plus E0 is 1.2 log 10 into P0 5 into 0.7 plus 3 into 1.8 plus that is P0, that is 4 into 1.8, this divided by what is P0. So, this is P0 again 5 into 0.7 plus 3 into 1.8. So, this is P0 plus delta P by P0. So, S2 will be equal to 0.55, 284.35 millimeter is 156 millimeter. This is the settlement calculation in stage 2, S2. Now, similarly, you can calculate settlement calculation in stage 3, that is S3 will be equal to U percentage into delta of 3. That means S3 is equal to U is 33 percentage 0.33 into Cc into H divided by 1 plus E0 log P0 delta P divided by P0, that means 0.33 into 0.243 into height 10 divided by 1 plus E0 1.2 log 10, and this is P0 is 5 into 7 plus 3 into 1.8 plus 4 into 1.8 plus delta P 5 into 1.8. This divided by P0 is 5 into 0.7 plus 3 into 1.8 plus 4 into 1.8. So, if you calculate, you can obtain the settlement in stage 3, S3 will be equal to 0.33 into 213 millimeter, that is 70 millimeter. So, now we can result and summary, it can be said that total height of the embankment in the first stage it is 3 meter, second stage 4 meter and third stage 5 meter. And degree of consolidation in the first stage 91 percentage, second stage 55 percentage and third stage 33 percentage. And period days is required, first stage 30 days, second stage 10 days and third stage is 5 days. Most of the consolidation takes place in the first stage, that means within 30 days you have achieved the major degree of consolidation, and then gradually you can see that degree of consolidation is decreasing with a minimum time or days. Settlement initially first stage 410 millimeter, then second stage 156 millimeter and third stage is 70 millimeter. Shear strength is ton per meter square, in the first stage 7.28, then second stage 9.3 ton per meter square and the third stage 10.83 ton per meter square. So, after this third stage, so total settlement we find 410 plus 156 plus 70, that means 636 millimeter. And you know that earlier we checked this settlement 563.49 millimeter, which we calculated in step 2. So, this settlement is greater than the 563.49, then it is okay. So, in terms of the settlement, and in terms of the bearing capacity, this is 10.83 ton per meter square, which is greater than 7.4 ton per meter square, what is required. So, it is also okay. So, we check in terms of the total settlement and in terms of the bearing capacity. So, it satisfies the criteria. So, design is safe. I will show you that Excel program for this design of the PVD. So, first that calculation of shape bearing capacity. So, you can put the input data cohesion 2.5 ton per square meter, bearing capacity factor 5.7, factor of FC 3. So, you can calculate. So, you find the shape bearing capacity is 4.7 5 ton per square meter. Next, you calculate the settlement. So, for the settlement is input data, thickness of the compressible clay layer is 10 meter, height of the embankment is 4.35 meter, compression index is 0.243, initial void ratio 1.2, bulk unit weight of the soil 1.7 ton per cubic meter, unit weight of embankment is 1.8 ton per cubic meter. Now, you calculate. So, you can obtain the output value of the settlement, that is settlement of compressible clay layer is 563.497 millimeter. So, you calculate initially what is the bearing capacity and then you calculate what will be the settlement. Now, we can design with the general consideration theory. So, we will first design with the general consideration theory. So, here design input vertical coefficient of consolidation, that is Cb in meter square per month is 0.334, average degree of consolidation U is 90%, thickness of the compressible layer H in meter 10. So, you can calculate, and this is the design output, time required for the given degree of consolidation in year 21.167 and time factor TB is 0.848. So, you see that how many years you have to wait to calculate. Now, and that is why we want to go for the design with the sand drain. So, you use the sand drain. So, here design input horizontal coefficient of consolidation CH in meter square per month is 6.5 into 10 to the power minus 2, average degree of consolidation U percentage 90, spacing of the sand drain in meter is 3 and diameter of the sand drain in meter 0.4 meter. So, you can calculate using sand drain. So, this is design output, the time required for the given degree of consolidation with sand drain in month with triangular pattern 59.384 month, and time required for the given degree of consolidation with sand drain in month with square pattern is 71.96 month. So, you see that even then if you introduce the sand drain, it takes about 59 month or 71 month. So, now we will adopt the prefabricated vertical drain, designing with prefabricated vertical drain. So, let us see what will happen if we use the prefabricated vertical drain. So, here design input horizontal coefficient of consolidation CH in meter square per month, that is 6.7 into 10 to the power minus 1, average degree of consolidation U percentage 90%, and width of the prefabricated vertical drain is 100 millimeter and thickness of the prefabricated vertical drain is 4 millimeter and PVD spacing is 1 meter. And now you can calculate and you can have the design output. So, time required for the given degree of consolidation with PVD in month triangular spacing is 0.97 month, and time required for the given degree of consolidation with PVD in month with square pattern 1.16 month. So, effective diameter of PVD D for triangular pattern, you know, 1.05 into spacing, that means 1.05, and for square pattern 1.13 into spacing, this is 1.13. So, you can see that how drastically can reduce the time when you use this prefabricated vertical drain. This is only 0.97 month for triangular pattern and 1.16 month for the square pattern. Now, design with prefabricated drain with mere effect and oil resistance. Most of the time we do not consider, but if we consider, then horizontal coefficient of consolidation design input CH in meter square per month is 2.8 10 to the power minus 1. Average degree of consolidation U percentage 50. Width of the PVD is 100 millimeter. Thickness of the PVD is 4 millimeter. PVD spacing is 2 meter. Diameter of the smear zone around the drain is 0.35. Length of the drain is 10. Drain spacing ratio is 30. Kh by Qw is equal to 0.001 and Kh by Ks is equal to 2. Now, if you calculate, so you can obtain the design output time required for the given degree of consolidation with PVD in month with triangular pacing is 6.24. So, if you consider the smear zone, now time required for the given degree of consolidation with PVD month with square pattern is 7.34 month. So, you can see that when you are using this smear zone is taken into consideration, you require more time. Now, the stage construction, this is important, that input soil property. So, thickness of the compressible layer is 10 meter. Maximum height of the reinforced earth wall H is 4.36 meter. Live load of equivalent to embankment H1 is 2.7 meter. And then here is the total height of the embankment 7.05 meter. Density of the embankment 1.8 ton per cubic meter. Density of the compressible soil 1.7 ton per cubic meter. Initial word ratio 1.2. Plasticity index 27. Horizontal degree of consolidation is 2.2 into 10 to the power minus 2 meter square per day. Vertical degree of consolidation and initial cohesionless soil is 2.4 ton per meter square. Compression index of the soil is 0.243 and factor of safety for safe bearing capacity is equal to 3. So, now this is the input soil property, and now if you design, so you can obtain the stage loading calculation. That means this is first stage, second stage and the third stage, and time required 30, second stage 10 and third stage 5, and total fill height is the first stage 3 meter, second stage 4 meter and then 5 meter. Then degree of consolidation 0.91 first stage, 0.55 second stage and 0.33 third stage. And initial cohesion value in the first stage 2.5, second stage 3.8 and third stage 4.9 ton per meter square. Then initial shear strength 4.75 first stage, 7.28 second stage and 3.3 is the third stage. Then cohesion of the shear strength 3.8 in the first stage, 4.5 in the second stage and 5.7 in the third stage. And shear strength in the first stage 7.28, in the second stage 9.3 and third stage 10.83, which is greater than 7.4 ton per meter square. So, this is in terms of the bearing capacity of the soil or improvement of the soil. So, total height of the field can be placed, that is 4 and 5 meter. And also it has calculated the settlement. So, settlement in the first stage 410, second stage 156 millimeter and third stage 70 millimeter. So, total settlement 636 meter. So, you can see that is 636 meter, which is less than the maybe he got in the second stage about 500 136 or like that millimeter. So, this also satisfy this criteria. So, we completed this Excel program for the prefabricated vertical drain and also prefabricated vertical drain with the smear effect and also the sand drain and without the sand drain. So, you find that there is a substantially reduce in time for consolidation if you use the prefabricated vertical drain. Next, I will study geosynthetic encased stone column. Now, load carrying capacity of the ground treated with geosynthetic encased stone column may be obtained by summing up the contribution of each of the following components under widespread of load such as tank, embankment and pavement, etc. A. Capacity of the stone column resulting from the resistance offered by the surrounding soil against its lateral deformation, that is bulging under axial load. B. Capacity of the stone column resulting from the bearing support provided by the intervening soil. And C. Capacity of the stone column resulting from increase in resistance offered by surrounding soil due to the surcharge over it. And D. Capacity of the stone column resulting from increase in resistance offered by confinement effect due to the peripheral geosynthetic encased stone column. Here you can see this diagram, this is geosynthetic encased stone column and this is the stone and this is the geogrid. So, here geogrid encased stone column and it has placed as a particular spacing. The number of research work also have been carried out in IIT Bombay using the encased stone column. I will just specifically focus only the one result using that encased stone column and this is the embankment. A. So, what are the theory have been adopted for this? A. Load carrying capacity considering the bulging action. Bishop Hill Mod 1945 provided a theoretical relationship between the limiting pressure sigma RL and the shear strength Cu. So, this is the sigma RL is equal to Cu into 1 plus ln Es divided by 2 into 1 plus mu into Cu. Now, Gibson and Anderson 1961 incorporated the effect of total initial lateral stress, that is sigma H0, in an elastoplastic material and modified the Bishop Hill and Motto 1945 and equation is sigma RL is sigma H0 plus Cu into ln Es divided by 2 into 1 plus mu into Cu. So, sigma of RL will be equal to sigma H0 plus Cu into K. Now, what sigma RL is limit pressure in a pressure meter and Es is elastic modulus of soil and Cu undrained shear strength of the soil and mu is Poisson's ratio and K is equal to 1 plus ln into Es divided by 2 into Cu into 1 plus mu. So, based on the field record, Houses and White's 1974 demonstrate that limit pressure sigma RL may be approximated to an acceptable solution replacing rigorous analysis solution as follow. That means sigma RL is equal to sigma H0 plus Cu into K plus U0, where U0 is equal to initial excess hydrostatic pore water pressure. Now, considering that the loaded pile behave as a pressure meter, houses ETL 1975, and the granular material in the pile approaches shear failure as well as bulging occur near top of the pile. The ultimate yield state Q ultimate on stone column is as follows. That is, Q ultimate is equal to Kp into sigma H0 dash plus K into Cu is equal to Kp into sigma RL, or U0 is equal to 0, allowing full drainage in the stone column. The above equation is interdependent on the value of A, coefficient of passive earth pressure Kp, B, total in situ initial effective radial state sigma dash H0, and C, that coefficient K. A, coefficient of passive earth pressure Kp. So, Kp is equal to tan square 45 degree plus pi dash divided by 2, where pi dash refer to angle of internal friction for compacted granular field in the stone column. It can be taken in the range of 45 degree to 55 degree, say 55 degree for Ramet stone column, that is like 1985. B, total in situ initial effective radial state sigma H0 dash. So, sigma H0 dash is equal to K0 into sigma of V0 dash. Sigma V0 dash is equal to effective vertical stress at depth Z, that is equal to gamma submerged into Z, where Z is equal to 4 into diameter of the stone column, that is at critical length of the stone column. K0 is equal to average coefficient of lateral earth pressure corresponding to undisturbed state of soil, that is at rest condition. So, most of the time that critical length of the stone column is occur within the 4 times the diameter of the stone column. There is a possibility for any bulging at that zone. So, that is why this Z value have been considered 4 into diameter of the stone column. Now, here that depend upon the soil type, you can select the K0. So, granular loose, then 0.5 to 0.6. Granular and dense, K0 value lies between 0.3 to 0.5. It is soft clay, K0 0.9 to 1.1. Hard clay, K0 0.8 to 0.9. And here is the remark. Thus, for the granular material, an average value of K0 is equal to 0.5, and that for the soft clay 0.9 may be taken for the design purpose. So, total initial effective radial stress sigma H0 dash can be considered equal to 2 into Cu, or can be obtained from limiting pressure strain relationship achieved from in situ pressure meter test houses ETL 1975. Now, see the coefficient K. So, you know K is equal to 1 plus ln Es divided by 2 into C into 1 plus mu, or K is equal to 1 plus ln into I of R. Now, IR is the rigidity index, that is basis 1972. Now, whether it is a medium, what would be the rigidity index? So, if it is a rock, rigidity index is 100 to 500, it is a sand, loose to dense 70 to 150, saturated clay, soft to steep 10 to 300, miscellaneous silt is 10 to 30, and mild steel it is 300. So, you can obtain this rigidity index by basis given by basis in 1972 depend upon the medium. So, whether it is a rock, sand, clay, silt, steel, so you can select this rigidity index value from this chart. Now, this IR varies between 10 and 300 for cohesive soil. The value of K will be between 3.33 and 6.7. Therefore, K value appeared to be reasonable for design purpose. The ultimate yield stress on stone column is given by Q ultimate is equal to Kp to K0 into gamma of sub into Z plus 4 into Cu. If some part of the column is not submerged, use bulk density for calculation. From the yield stress obtained above, shape load capacity of the column may be determined using the factor of safety is equal to 2, where D is diameter of the stone column. So, therefore, Q1 is equal to Q of ultimate by factor of safety into 5 by 4 into D square, where D is the diameter of the stone column. So, you can calculate the Q1 from this equation. Now, B, bearing support provided by the intervening soil, that is bearing capacity of the soil is given by Q ultimate is equal to C into NC. For the clay, pi is equal to 0, NC is equal to 6. So, therefore, Q ultimate is equal to C into 6. Therefore, Q shape will be Q ultimate 2 divided by factor of safety. As factor of safety is equal to 2 as per BIS 1997 is considered admissible in view of the strength gain in case of tank, embankment and subgrade, etc. So, shape load taken by the surrounding soil, that is Q2 is Q shape into AS, where AS is equal to actual area of the soil surrounding a stone column. So, let us consider the triangular pattern of the stone column having a spacing S between them. So, AE is total influence area including the column is equal to S into sine of 60 degree into S, that means 0.866 S square. Area of intervening soil for each column is given by S will be equal to 0.866 S square minus pi d square by 4. Therefore, shape load is calculated at Q2 is equal to Q shape 2 into 0.866 S square minus pi by 4 into d square. Next, surcharge effect. Due to load, when the stone column dilate, some parts of the load will be shared by the surrounding soil. Consideration of soil under this load result in the increase of its strength, providing additional lateral resistance against the bulging of stone column. The analogy for expansion of the cylindrical cavity, that is basis 1972, and bulging failure phenomena of granular pile in a homogeneous, isotropic and infinite soil mass has been used to find increase in capacity due to the additional soil resistance. Now, increase in the means radial stress, that is del sigma r dash. So, del sigma r dash is equal to Q shape 2 divided by factor of safety into 1 plus 2 K0. So, increase in the ultimate cavity expansion stress, that is delta sigma R0 is equal to Kp into delta sigma R into Fq dash, where Fq dash is the basis 1972 dimensionless cylindrical cavity expansion factor, and it depends upon the pi and the reduced rigidity index. For when pi is equal to 0, F dash Q value is equal to 1, as mentioned basis 1972. Therefore, increase in the yield stresses will be equal to Q ultimate 3 will be equal to sigma del sigma R0 into central cross sectional area of the stone column. So, allowing a factor of safety is equal to 2 to account for various Sn in K0 Cu and cross sectional area, the increase in permissible load of column, that is Q3 will be equal to Q ultimate divided by factor of safety into pi by 4 into d square. Now, D, what will be the effect of geosynthetic encasement. Now we will study what is the role of the geosynthetic encasement. Now geosynthetic encased stone column analog to the thin cylinder. So we are considering a thin cylinder where D is the internal diameter and T is the thickness and L is the length and P is the internal pressure intensity. So we are considering as a thin cylinder. It is analog like a thin cylinder. Also thin cylinder also flexible and geotextile material also flexible. Let us consider a longitudinal section XX through axis dividing the cell into two halves, A and this A and this B. Now let us consider two elementary strip and subtending at an angle of delta of theta. At the center at an angle theta, either side of the vertical through the center. This is Ramamutan and Narayan is 2008. So we can have the normal force acting on each strip is given by delta Pn is equal to P into R into delta theta into L, and resultant of the two normal forces on the two elemental strip acting vertically, that is normal to XX, is delta P is equal to 2 PR delta theta into L into cos theta. So total force normal to the XX on one side of the XX is equal to total bursting force, that is P is equal to integration 0 to pi into 2 pi RL cos theta into del theta. So which we are having from here. So you can have P is equal to 2 into R into L into P, where P is the projected area into intensity of radial pressure. Let F1 is the intensity of tensile stress induced in geosynthetic material across section. The resisting force offered by the section is equal to F1 into 2 into L into T, equating the bursting force to resisting force. That means F1 into 2 into L into T will be equal to 2 into R into L into P. So hoop stress, that is F1 will be PD by 2T, or P is equal to 2 into T into F1 divided by D. Now longitudinal stress is given by for geosynthetic casing, let us say F2 is equal to 0. So F2 will be equal to P into D divided by 4 of T. Now greatest shear stress Q maximum is given by Q maximum is equal to F1 minus F2 by 2, that means equal to P into D divided by 2T. Now you know what is circumferential strain, that is the ratio of change in circumference to original circumstances, where epsilon 1 is circumferential strain. So epsilon 1 can be written pi into D minus delta into D minus pi D, that is change in the circumference. This divided by original circumference is pi D. So this will give delta D by D. Also circumferential strain can be expressed as epsilon 1 is equal to F1 by E minus F2 by M into E, where E is the Young modulus and L by this M is the Poisson's ratio. So epsilon 1 is equal to F1 by E is equal to P by 2 into D divided by T into E, where P will be equal to epsilon into 2 into T into E divided by D. So, the developed resisting force for a given strain, so P of fabric is equal to P by T, that means P 2 into E into epsilon 1 by D. Therefore, shape load carried Q4 will be equal to P fab into Kp divided by Fs into pi d by 4, where factor of safety may be taken as 2. So, what is the total shape load carrying capacity of plain and ordinary stone column? That is, Q shape will be equal to Q1 plus Q2 plus Q3. Now, total shape load carrying capacity of NK stone column, that means when you are using this geosynthetic material. So, Q shape 2 will be equal to Q1 plus Q2 plus Q3 plus Q4. So, you know that how you have to calculate that Q1, how to calculate Q2, how to calculate Q3, and then also you know how to calculate the load carrying capacity for the geosynthetic material, that is Q of 4. So, Q shape 2 will be equal to Q1 plus Q2 plus Q3 plus Q4. So, total number N of stone column required, N will be equal to total load divided by Q shape. So, area per column is given by Naik 1985, that area per stone column is equal to area of the load divided by N. So, area of the load, it may be the tank or embankment, etc., that divided by N. So, required spacing of the stone column for triangular pattern, that is S required, will be equal to root of area per stone column divided by 0.868. We have made a several design chart for the in-case stone column. Only in this course, one of the design chart is given here. So, here C value considering 10 kilonewton per meter square, pi value 35 degree, spacing 1.5 meter, gamma charge as 5 kilonewton per meter cube, and then bearing capacity of the plane and the reinforced stone column is given. This is the stone column diameter, it may be 0.5, 0.6, 0.7, 0.8, 0.9, 1, 1.1 and 1.2 meter, and this you know that Q1, Q2, Q3 and Q4. So, you can see that for a particular the stone diameter, let us say that when the diameter is 1.2, so Q1 you are having that bearing capacity 128.54 for Q1, Q2 24.53 and Q3 is 87.64 kilonewton and Q4, that is due to the geosynthetic material, the 34.78. So, total Q shape 1 is 240.71 and Q shape 2, this is for this geosynthetic material, it is coming for 275.4 of 9. So, you can have some idea that what will be the how you can increase the load carrying capacity of the NK stone column. So, if we introduce that geogrid or geotextile which is may be made of the polyester or the bamboo geogrid, then the load carrying capacity can be increased. And there are many the design chart for the defined value of Cu pi and defined spacing, and here as I mentioned that only one chart has been given. So, you have some idea that how you have to calculate that load bearing capacity in a NK stone column and what are the theory also have been adopted. What are the structure theory, how it can be incorporated as an analog in the geotechnical engineering. So, from the encasement, different types of the encasement can be prepared using geosynthetic reinforcement. Bamboo is easily available and cheaper in India with respect to polyester geogrid and also environmental friendly. Natural bamboo geogrid encasement can be prepared to encapsulate the stone column. Narrow bamboo stick of 10 millimeter with proper finishing were collected to prepare the bamboo encasement. This is given by Datta and Mandal 2012, and plenty of the bamboo are also available. And here you can see that some of the bamboo encasement which is made of the encasement wrap with the jute geotextile material. Also we are made with the geogrid, with the polyester geogrid encasement material. So this is one of the bamboo that they are geogrid. This is the geotextile material, and this is the bamboo. So you can make a bamboo encasement that is wrapped with the jute geotextile material. And number of the tests also has been also carried out on this with this material. And because this is one of the bamboo material which is plenty is available, and also its growth is very fast. So you can say that environmental safety, in terms of environmental safety, this is no problem, because this is one of the that plant which grows fast, very fast in the world with respect to any other plant. So growth wise, production onujai, there is no problem, and it is also the eco-friendly. So one can make use of the bamboo as a geogrid material, and we will observe here that what are the properties of the bamboo, how you can introduce the bamboo as a geogrid, bamboo also as a form of the mat form. So we have also number of tests also have been carried out using this in the form of the mat. So you can use as a mat form. So it can be come in, it can come and contact with the soil, and it's give very good tensile strength material. So lot of the research work has also been carried out in IIT Bombay using the bamboo material in different shape and the size, including the plastic, waste plastic material. So now we will study that some tensile strength of the bamboo geogrid was determined according to the ASTM D4595511 specification for wide width strip method. Because wide width specimen of 200 millimeter, this is the width is 200 millimeter, and 100 millimeter is the gauge length was prepared by attaching the narrow bamboo strip from both direction with adhesive. Now this is the test have been performed. This is why the bamboo geogrid specimen. This is the before the tensile test, and this is the after tensile test. You can see that what is the behavior of the bamboo geogrid before and the after, and how it also fell. So because we are also equally comparing with the polyester geogrid, this is wide width tensile strength of the polyester geogrid with the same specification, and you can see some also the result, the tensile strength versus the strain curve. For A is the bamboo geogrid, and this is the polyester geogrid. So there is a substantial improvement of the tensile strength of the bamboo geogrid. You can see it gives about the 100 kilonewton per meter, and in case of the polyester geogrid, it is about 30 kilonewton per meter. But you cannot compare with this geogrid with the bamboo grid at this present stage, because the configuration, size and shape is the different. But overall you can have some idea that there is a improvement of the tensile strength of the bamboo grid. So, properties of the geogrid here shown that bamboo geogrid, that mesh size is 5 millimeter into 5 millimeter, ultimate tensile strength is 110 kilonewton per meter, and ultimate stiffness is 2200 kilonewton per meter. Polyester geogrid, the mesh size is 5 millimeter into 5 millimeter, and ultimate tensile strength is 32 kilonewton per meter, and ultimate stiffness is 160 kilonewton per meter. Now, this is the axisymmetric finite element model of encased stone column after Datta Mandal 2012. So, this is the stone column, this is about 100 millimeter in diameter, and the length of the stone column about 500 millimeter. This is geogrid as an encasement, and this is prescribed as a displacement, that is 200 millimeter of diameter. This is the horizontal fixicity, and this is total fixicity, and this about 425 millimeter, and this on the clay soil sample. Now, let us see that what is happening effect of the encasement stiffness on radial deformation. So, this is the radial deformation with respect to height. So, here is ordinary stone column, this is dot is the ordinary stone column, and ESC is the encased stone column, which is 160 kilonewton per meter, and also the encased stone column is 2200 kilonewton per meter. So, here we have used the bamboo geogrid, stiffness is 2200 kilonewton per meter, polyester geogrid 160 kilonewton per meter. So, what is the radial deformation of stone column without and with the encasement from the finite element method? You can see that here, that in case of the ordinary stone column, you can see the deformation is much higher with respect to the encased stone column. So, this encased stone column also depend upon that what will be the tensile strength of the encasement or material or reinforcement material. You can see that how this is substantially is deformation is decreasing with the height for the inclusion of the reinforcement, and then depend upon that what will be the modulus of elasticity of the material, what will be the tensile strength of the material. So, more uniform and minimum radial deformation is obtained with increasing the stiffness of the encasement. Ordinary stone column OSC fell by bulging within almost 2D length of the column with a significant radial deformation of around 13 millimeter, whereas using polyester geogrid and bamboo encasement, radial deformation reduces to 4 millimeter and 1.5 millimeter respectively. So, you can see that compared to the ordinary stone column where deformation is 13 millimeter, but in case of the polyester geogrid is 4 millimeter, in case of the bamboo geogrid it is 1.5 millimeter only. So, you can observe that how the radial deformation is drastically reduced for the inclusion of the polyester or bamboo as a geogrid reinforcement material. Of course, it depends upon what should be the stiffness of the material. Now, geogrid encasement provide excess lateral confining pressure to the column and prevent its radial deformation. as the stiffness increases, more hoop tension gets generated in the encasement and it provides more confining pressure to the stone column. So, here so far we have studied it that in case of the stone column, how you can design and what are the design steps has been taken into consideration and how the structural plate thin state theory has been analoged with this encased stone column problem, and also that natural material like a bamboo geogrid material, how it can be incorporated, and we find that how its that stiffness also has increased and the deformation or radial deformation has been reduced with respect to the ordinary stone. So, there is a potential use of the bamboo geogrid as a reinforcement in India and some other parts of the world. So, with this I finish my lecture today. Let us hear from you any question. Thanks for listening.